Hello, everyone, and welcome to NASA's resident office at Vandenberg Air Force Base in California. I'm Steve Cole from NASA's headquarters, Office of Communications. Welcome to the 29th NASA Tweetup. We're here on the occasion of the launch of the NPP satellite, that stands for the NPOS Preparatory Project, from Vandenberg later tonight, early Friday morning. NPP is NASA's first climate and weather satellite. We've launched a lot of satellites doing Earth science from Vandenberg, but this is the first one designed to do both climate observations and weather satellite observations. So we're really excited to have everybody here for the Tweetup. We've got a big day of activities. It's a really nice day outside today. And the weather forecast for launch tonight is looking really good. So everything's moving forward. We've got a full day of activities planned for the Tweetup today, and launch is scheduled for just about 17 hours and 15 minutes or so from right now. So if you want to follow along on Twitter, the hashtag for the Tweetup is hashtag NASA Tweetup. You can also follow the activities online at www.nasa.gov/NPP. There's a lot of videos, photos, and we'll even have live launch coverage on the website later tonight. In the next hour and a half, you're going to be hearing from 5 speakers who work on the NPP mission and also do a lot of interesting Earth science that NASA is pretty well known for. Most people, however, know NASA as getting people into space, making amazing discoveries about the solar system and the whole universe. But not as many people are as aware of all that work we do on Earth, looking at Earth, trying to better understand what's going on with Earth so we can understand what our future will be here on the planet. To give you a quick overview of some of this and the mission, I've put together a 1-minute video that will roll in just a second to give you an idea of the mission and how we study and what NASA does to study planet Earth. So if you could roll the video. NPP will join over a dozen NASA satellites zipping around the planet. What they show us is global, like temperature of the oceans, chemical makeup of the atmosphere, and the pulsing life of our planet's biosphere on land and in the oceans. They also zoom into detailed things like hurricanes and wildfires, coral reefs and ice sheets. And here's NPP, which is going to take us into the future with a multi-talented suite of instruments. The next stage of NPP's journey begins tomorrow morning with a ride into space on a Delta II rocket. The trajectory takes it south over the Pacific as it climbs into its pole-to-pole orbit. There, NPP begins its work life collecting round-the-clock data critical to climate research and weather forecasting here on Earth. Our speakers will give you a lot more detail about the mission and the Earth science research that NASA does. So let's start with our first speaker. First speaker is astronaut Piers, who is currently Deputy Director at NASA Goddard's Science and Exploration Directorate. Now, Piers is a unique NASA employee in that he I think just over a year ago, he was in space on one of the space shuttle missions, and he does Earth science research at NASA Goddard Space Flight Center, which is in Maryland. His research focuses on the interaction between Earth's biosphere, the land, the oceans, and the atmosphere. He's done field work in such places as Russia, Africa, and Brazil. And Kansas, distant Kansas. And he's going to talk to us a little bit about why NASA does Earth science. Piers.
Good morning, everybody. Good morning. I think I have to keep everything to 140 characters or less, right? Okay. I'm very glad to see you all here today. I'm very excited about this mission that's coming up. Couple of things. Before I went off to the astronaut corps, I was like him. That's Jim Gleason, who's the project scientist for this platform. But for an earlier version, the EOS Terra, not Terror, Terra, T-E-R-R-A platform, that was launched in '98 from here, from Vandenberg. And that was a large polar orbiting satellite that was monitoring the Earth's, total system, atmosphere, oceans, land, ice, biosphere. NPP hopefully will continue the tradition because Terra and Aqua, the sister platforms, are getting a bit long in the tooth. And we're hoping that they're going to last for 2 or 3 more years, but who knows. So NPP is arriving in the nick of time. Why do we do what we do? Why do we do what we do? I feel like Elvis here. I know. Why do we do what we do? NASA can make a really unique contribution to the whole business of climate science. You know, from your perch up there in orbit, mapping the whole world in one day, which is what NPP will do. It'll provide wall-to-wall imaging of the whole world every day. And it's such as a really clever trick. When you launch from California, you can map the world while it's sunlit, because you kind of chase the sun around the world. It's really ingenious. And these data are going to be essential for basically understanding climate change, looking at small changes over years and decades, and trying to understand what's going on. So with that, I'm open for questions, or what do we do now? Do we go straight into Jim? Yep. Jim, your turn. No, questions, all right. I thought I was going to get off the hook. Questions, don't ask me anything really, really hard.
Be sure to wait for a microphone if you've got a question. Questions?
So I know that NPP is often described as a risk reduction mission, a preparatory mission, but it's also talked about as a replacement for an aging Terra and Aqua. It's got, which one is it more of as far as NASA is concerned?
I think it's both. It's got 4 new instruments on it, so which are meant to be the pioneering sort of marks of instruments that will be used on successive platforms into the future. So I guess the first of anything is risk reduction, right? On the other hand, it would be bad or not good if this didn't work out for us, because it's unlikely that Terra and Aqua will last until the next in the series. So yeah, these are the first, operational versions of these instruments.
Other questions? How did being an astronaut in space change your view of Earth?
Oh, well, no radical changes, just a few very nice surprises. It's beautiful to actually watch see the world through your own eyes once around every 100 minutes. It's really quite a thrill. One of the things that surprised me, I spent a lot of time studying the atmosphere and modeling, and I thought I knew everything, But I was surprised when I got up there how thin the atmosphere is. It's really, really thin. It's like an onion skin around the world. And all the systems that you see, like hurricanes, they're very flat. They look like basically slicks of oil on a puddle when you see the very, very thin systems spread on this very, very thin layer. So that was a kind of surprise for me.
I just wanted to ask, what hurricane did you see?
I can't remember. It was a big typhoon in the Pacific.
Oh, okay.
I could have named it. I don't know, because no one else had yet, I think.
Leah, is anybody asking questions online? Take any questions from NASA Tweetup hashtag? Anyone watching at home? Emily, you have another question?
Sure. I know that Terra and Aqua orbit at different local times of day. NPP is only going to be at 1:30. Is that going to replace the capability of having 2 satellites in orbit? How can NPP replace both of those?
It can't replace both. Terra is a morning satellite, 10:30 I think, and Aqua is afternoon, 1:30, and this is 1 o'clock, 1:30. Okay, so I'm not sure when there will be a series of NASA research satellites scattered around during the daytime. I'm not sure when the next morning satellite is projected to launch.
The main satellite that'll be picking up from that would be essentially the European MEDOP, which is at 9:30, and they're currently flying AVHRRs, but in the JPSS 1 time frame, the next generation will have a MODIS-like, VIIRS-like imager on the next generation European satellite in the morning.
Gotcha. So this is really filling the Aqua slot. Yeah.
Other questions for astronaut Piers Sellers?
Please talk closer in the microphone. Okay. Could you please explain for us old dummies what the 1:30 and the 9:30 thing means? Does that mean it's? I don't understand the timing.
The orbit's designed so that when you're flying around the world, underneath you on the daylight side, that is the time of day as the satellite comes over. And it kind of chases the sun. It's called sun synchronous. It kind of chases the sun around the planet. So approximately, that's the local time of day when you're imaging on the day side.
Okay, we have a
Very clever, I think. It took me quite a while to understand how it works.
Hi, I was just curious, having worked on Terra, what has impressed you about the data that it's brought back to Earth, and what are your feelings knowing that it's aging and going into retirement?
Well, you know, I have feelings in common with Terra, of course. No. I can't afford to retire, though. A couple of things I think that came out of Terra that were really super. One was the MODIS instrument, which is this beautiful instrument that maps the whole world at 250-meter resolution, but every day. And that's been an astounding success for all kinds of science, you know, oceans, land, atmosphere, ice, the lot. It's been a real home run. So the two MODIS instruments, one on Terra, one on Aqua, have done really good service. The other thing is that on Aqua, and I'm going to change here a little bit, on Aqua there's a sounder suite that profiles the atmosphere temperature and humidity and stuff like that. And those data have been really very useful for operational weather forecasts. So we got our money's worth.
Any other questions? Okay, way in the back. Let me get back there.
Having been to space, how do you feel about the commercial space industry and space tourism?
Well, having been to space, I wish I could take everybody with me. So, you know, it's that much fun. So I wish them well. When I go, I don't have the money. So maybe one day, who knows? Keep saving. I think you should go. Very good.
Any other questions? All right, over here.
I've got a question from Twitter. What does it sound like to astronauts inside the ISS when astronauts are working outside during a spacewalk?
It sounds like a bunch of rhinos banging around on outside the hull. You know, when they're working on the pressurized segment, you can hear them bang, 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 going all the way down, clattering with all their tools, and then bang, bang, bang all the way back. So you generally know where they are. And you hope they're not doing anything foolish with drills or anything.
Question over here. Okay.
Hi. I've heard that space smells like something. Do you know what it smells like? And could you describe it?
The Russians talk about this smell of space. When people come back in from a spacewalk and you pop them out the airlock and still in their spacesuit, there's a smell which to me smells like roast pork or maybe bacon. And and the Russians said, oh, zapach kosmosa, which is the smell of space. But, you know, bacon or whatever it is actually just some material boiling off the suit, we think. It goes away after a while.
Actually, on that note, I want to know more about the food that you have to eat in space.
Right, this is the last one I'm going to do on the astronaut thing, and we're going to go back to NPP. Just have to do that. That's all right. Yes. Food's not bad. The food would be really great if your taste buds worked okay in space, but they don't, you know, because of the gravity shift and stuff. Everything tastes like cardboard. So, you know, people take up a lot of Tabasco sauce with them to make things bearable. There you go.
Okay,
back to NPP.
Any other questions? NPP, Earth Science. Oh, here we go.
So I go to Terra and Aqua all the time whenever there's a wildfire near LA, and I'm wondering how NPP will improve on their capability to monitor wildfires.
Well, NPP, the VIRS instrument, has a fire channel. So you should be able to keep track of the fire in your back garden still. And I think there'll be a continuing fire product that'll go more or less seamlessly with the one from Terra.
Will its resolution improve on Terra and Aqua's?
About the same. How big is your yard?
I had a question. Piers, the work you did in the field in exotic places like Kansas, Russia, Africa, what were you doing? What were you studying down there?
Well, we started off trying to model interactions between the land surface and the atmosphere to improve our climate models, and we found out we weren't doing a very good job. So go out to the field and measure the stuff. So what we would do is measure interactions between the surface and the lower atmosphere with all kinds of little instruments on the ground, and then fly aircraft over it to integrate over a large area, and then time it all so that you were doing that when a satellite came over that you were interested in. And the idea was that if we could make it all work, we could use the satellite to spread that information globally. And it really worked. We improved the models and managed to spread all the data globally using the satellites. A lot of fun.
Thank you. Any other questions for Piers? Okay. Well, thank you, Piers.
Thank you.
Give a round of applause there. Okay, our next speaker is Jim Gleason, and he's the NPP project scientist. So he's the head scientist for the whole mission. He also works at Goddard in Maryland, and his research expertise is atmospheric chemistry, ozone layer. Did some work with the Mount Pinatubo eruption when that went off several years ago. Made a big impact on the globe. So he's going to talk a little bit about NPP, how it's going to be used for both scientific research and practical applications here on Earth. Thanks, Jim.
Okay, thanks. Can we go back to the hold of this one by any chance? So it doesn't loop for a minute? Or is it just going to loop? So is it better to work off the video monitor or to hold up the small model? Okay. NPP, flying along, as we said. We have 5 instruments. Let me rotate the deck here. Okay. Large instrument on the front is our imager, VIIRS, and there'll be a test on this later on what every acronym means. Visible Infrared Imaging Radiometer Suite. Okay. That should fit in a tweet. Barely. VIIRS. All right, this is a 22-channel instrument that basically takes all of the, I'm going to cast aspersions on, all of the really cool pictures you see generally are from an imaging instrument. They're from MODIS. There we go. That's the VIIRS instrument there. 22 channels at 2 different resolutions, 350 and 750 square kilometers, and basically that's what takes all the cool pictures for you. NPP is essentially a continuation mission. It's an extension of what we learned from NASA research missions shown to be how valuable it was and worth continuing for a lot of different reasons. And one of the operational weather satellites are satellites that have to go. They launch on a regular schedule. They're critical things. So we were just about in time for essentially the generational upgrade of the weather satellite instruments and system. And to do that, we essentially launched the EOS missions, very complicated instruments, lots of them, to see what really worked, what was interesting. And essentially the best of that, or the most useful suite of that instruments, has been distilled down into the NPP platform. So we have the VIIRS instrument, which is a little smaller than MODIS, has less channels, but really has the sort of optimum suite for doing the things that need to continue. The next 2 instruments are the CRIS, Cross-Track Infrared Sounder, and ATMS, the Advanced Technology Microwave Sounder. The CRIS instrument essentially is a infrared spectrometer. It takes the infrared spectrum of the Earth. And the advance that EOS made was that prior to that, the infrared instruments on the polar orbiting were discrete channels. So you had 5 or 6 channels, and that's how they would do the temperature measurement. The AIRS instrument on the Aqua satellite was the first one to take essentially the complete spectrum for doing research. We had measured the Earth's infrared spectrum before on the Nimbus 4 satellite between 1970 and 74, and we didn't get back to it until the AIRS instrument, which was launched in 2002. So since we've learned everything about sort of how having that more spectrum, more channels really improves both the temperature and more importantly, the water vapor profile, the water vapor distributions. And that's coupled to the advanced technology microwave sounder, which is a microwave instrument, so it also measures temperature and moisture in the microwave region. And the great thing about the microwave instrument is it's not sensitive to clouds. So you can see around and through clouds. So the combination of the infrared, which has better vertical resolution, but you can't see around clouds. And as you guys know, interesting weather occurs around clouds. So it's a little, you're sort of one of these betwixt and betweens. I get really good resolution, but I can't see through it. So you couple it with a microwave and you really do that. The cool thing about ATMS is it's essentially the same instruments, the same data as 3 instruments on the Aqua platform. So essentially they've taken 3 boxes and put them into one. And if you're trying to put things in space, real estate, mass, power is really, really expensive. So you can get, if you can get the efficiencies of putting three boxes in one, everyone likes that. On the aft, right there facing backwards, is the OMPS instrument, which carries on the ozone layer measurements. Has 2 instruments on it, one that looks nadir, which basically carries on the TOMS and SPUV maps of the ozone hole that you guys have been seeing. And then there's the limb instrument, which Scott talked about, which actually measures the limb, which is that kind of blue line right there between the white of the clouds and the dark of space. That's essentially the atmosphere scattering the sunlight. And the OMPS limb instrument just looks at that little blue line and measures the amount of ozone in that little blue line. And that's how you get a very good way of measuring the vertical distribution, how the ozone changes between the surface and space. And then the last instrument is the series instrument, which is basically our energy balance instrument, which looks at how the energy coming back from the Earth is distributed in the visible and in the thermal infrared. So if you're trying to understand constant solar input, how is the surface and clouds changing in terms of the energy balance, to understand what's happening in terms of how clouds and surface affects the entire energy balance and where heat is going in the Earth. So that's our 5 instruments. We have over 30 direct data products that are made by the ground system, which then fan out to different weather centrals, and each of the weather centrals does their own custom processing of different specialized products. So product counts are kind of a nebulous thing in terms of how do you want to do the bookkeeping, but it's over 30 different direct products from the data processing system that we have. That's done in essentially almost sort of real time. There's a downlink every orbit, and then the data products are out about 40 minutes after the downlink at Svalbard. And then they go from the weather centrals direct to the weather centrals, and then all the data goes to an archive, which is the National Center for Climate Data Record, National Climate Data Center, and you guys can log on to your class system and get the data probably 2 hours after it's taken. So that's what NPP does. It's both, so if you sort of take a top level, NPP makes observations that are used for a lot of different applications, almost anything you can think of on any kind of time scale, from weather, which has to be done right now, smoke, fire, floods, right now, to essentially using NPP data to add to long-term data records to see have things changed from now to where they were in the past. And the other critical thing, the reason why we spend a lot of time on this, NPP data is one of the few data sets that actually gets more valuable as it gets older. Because what we're going to be looking back is people who are going to be looking at, JPSS 3 and 4 and looking at multi-decadal records in 2040. And they're going to want to look back and see what were those instruments, how are they calibrated, what's going on, and really understand what those measurements were. And that's one of the advances we've done when we talk about making a climate instrument. It's characterizing and calibrating an instrument, so when you look back on that data, you can really understand what's going on. We spend a lot of time in my group trying to understand ozone from the Nimbus 4 instrument, which is in 1970, and we don't have a lot of data. We have the actual data, but the calibration, the measurements, all of the support things that went along with it aren't there. And that affects the quality of our analysis. The data is what it is, but trying to understand it and put error bars and try to see, was it the instrument or were the ozone levels really at that time in 1970s. So as we go forward, NPP, EOS, really that careful characterization and calibration of the data, putting it all in the archive makes it incredibly valuable for future researchers in the next decades. And I'll be happy to answer any questions.
Okay. Any questions for Tim? Hold on.
Yes, 2 questions. From the time somebody conceived of this satellite that's going up tonight, how long ago was that? And how soon after launch is it actually operational?
Satellites have very long gestational periods. I would say probably in the late, it was sort of formalized probably in the late 90s, but probably in the early 90s, as EOS was starting to get reach. It's hadn't been launched yet, but on the path for launch. What was going to follow EOS, and then if you look at the flyouts of where, how many post satellites there were, people were looking at sort of probably doing that in the early 90s. Probably really got to the end pose was in the Clinton era. August 98 was sort of the Easton workshop was sort of the formal decision that NASA should work with NOAA and figure out how to infuse the EOS observations into the next generation of operational measurements. When will NPP data be operational? Sort of a spectrum. It depends the complexity of the data product and the performance of the instrument. So we have brand new instruments, brand new spacecraft, brand new ground system. Everyone's a little, don't want to give exact things, but I would say for a straightforward instrument like the microwave radiance, which is a critical, measurement that the forecasters want, we do satellite checkout for 90 days. I would expect to see, absent any major issues with the instrument, the first use of ATMS data probably another 90 days after that. No, that would be 60. No, 6 months. Sorry, you're right.
And how long does it take to build it?
This is not a traditional satellite. Okay, this is the bus took 3 years. ATMS probably took 3 years. Veers, Chris were closer to 8. So this was a development in a brand new programmatic approach, and it took longer than expected.
Okay, other questions?
So knowing that you're sending this very new satellite with a lot of new technology up to orbit on top of a very old and tried and true rocket system, when will you personally be the most nervous? Launch time, or once the satellite starts to go through its checkout and the data starts coming in?
You never stop being nervous. It's like children. They move out, but you still worry about them. No, I mean, having had a some less than successful launches recently. Everyone is, of course, nervous. But there's a lot of confidence in the Delta II. I think that's one of the great things about this is it's the Delta II. It's an excellent team. It's still a rocket. You know, I think the ULA motto of one launch at a time is actually the right way to think about it. 150 successful ones previous performance is no guarantee of future success. But very serious team. They work real hard at it, and I think we're all, you know, we all take a lot of comfort in the fact that this is a very successful launch vehicle with an excellent team. So.
Since it takes 8 years to build this, what do you do with advances in technology as they happen? Do you try to keep up with that, or is it planned and you go right ahead?
Advances in technology for space things is a little tricky because you want to be just a little bit backwards, a little bit back, because we're going to launch it. It's got to last 7 years in space in a hostile environment. You really want to understand what's going on. So for these operational missions, which have very long lives, you tend to be not bleeding edge because you want to know that things really work. And there's a very complicated qualification process for parts and systems and things like that. So we do take advantage of technologies, but we're not always at the cutting edge because we want to make sure that they can actually work in this environment for the length of time that we want to do things. So we have fairly advanced technology, but I'm not sure it's like completely bleeding edge.
Okay, another question in the back.
Hi, can you give an approximation of how much data volume the NPP will produce in about a day?
We do sort of the generic, if you were to say, I need to get all the NPP data, you would sort of have to do the sort of quick rule of thumb is about 4 terabytes a day. You know, is what you would have to have a dedicated line for and storage for and all that. You can proliferate beyond that depending on the volume of things you want to do and extra special products and how much other things but if you were just a generic user, 4 terabytes would get you the, you know, pretty much everything.
I just joined NASA in February of this year, and before then I worked with the U.S. Coast Guard, and the last almost all of 2010 was spent in the Gulf of Mexico working on the Deepwater Horizon oil spill. One of the most invaluable tools that we had as we were working through the daily cleanup operations was satellite imagery that was coming in from NASA and NOAA that gave us a better real-time operational picture of where the oil was in the maritime environment. Does this system that's going up have that same type of capabilities? I don't know which satellite was feeding us at the time.
Yeah, the pictures you were looking at were MODIS pictures, and they were either from Terra or Aqua, probably depending on either both, and depending on what you're looking at, would just be depending on what the local cloud cover was. But yes, we have, in those channels, we have the same imagery, and it's about the same physical resolution. So you will get that same data as well. Mm-hmm.
Thank you. Other questions? All right.
I was just wondering, what are some of the tests you put the satellite through before sending it into orbit, making sure that it'll, you know, work properly?
We do a whole. Everything is tested. Okay, so we start with an instrument is built up of lots of little subsystems. All those subsystems are tested. Do they work? They get put together, and then the instrument is tested as a whole. Does it all work? And then the instrument is calibrated. So it goes through a thermal vacuum test to make sure that it can stand the thermal cycling in space. It's shaken, so it goes on a shaker table, so it goes, you know, backwards, forwards, and up and down. Does what's called EMI, electromagnetic interference, to make sure that it's not picking up things from other things. All of the data sets, all of the data formats, all of the output is checked. Readers, do your readers work? You know, have you got the right drivers? All the standard stuff. That all goes, that's all tested. It all goes on the spacecraft. and essentially that whole testing cycle is repeated. You saw, I don't know, it was on this one, instruments are bolted on, they are, you go through a vibration, you do acoustics, where essentially they bring, literally it's Maryland Sound Systems, the same guy that same people that do rock concerts come and they put the great wall of speakers next to it and they blast it with sound because the launch is extremely noisy. So can it withstand that type of vibration? You do EMI, EMC to make sure the data from signals from VIIRS aren't coming up on the ATMS, line. Another thermal vac, and then all of this is coupled with ground system tests. So essentially, there's a complete ground system test. So the data comes down in Svalbard, Norway, and what they do is they take an RF transmitter, they put it on the other side of the fjord, and they beam RF data to Svalbard, send it through to NSOF, and then back to the satellite at Ball. So there is a complete end-to-end test of the ground system. And then the ground data processing system goes through all the tests to everybody, all of the users at NOAA, users at the Air Force, the archive. Does the archive get the data? So there's a complete end-to-end testing, and we've been doing this, the whole end-to-end testing, for about 18 months now. And, of course, there's lots of paperwork. And you laugh, but that's what keeps it all, does the file format meet the description that, you said it did? And when it doesn't, there's meetings.
That's your punishment, right? I know how funding for scientists works on deep space missions, but I get the idea that it's different on Earth missions. Who gets funded to do research with the data, and where does their funding come from?
The funding for scientists is pretty much the same. People write proposals, and they're competitively chosen, and you get to analyze data. If this were a NASA mission, you would be competitively selected for the instrument and or for the science team. So, when I did my OMI NO2 work, I wrote a proposal and I was chosen to make the data product, and we make the data product, and the original one was a 5-year proposal, and now we're on 3-year proposal cycles. So basically every 3 years, people write a proposal for continuing to do the work, and then there's money to do science, which is also on a 3-year cycle as well.
I've got another question from Twitter. How are the JPSS satellites better than the EOS satellites at understanding, monitoring, and predicting what happens on Earth?
Better. I would say they're going to be better because they're going to keep on going. And that's really the key thing here, is it's not better as in new and improved. It's the longer we take these excellent measurements, the more we learn. And the more we look for changes. So because it's an operational system, you don't see dramatic improvements. I mean, the current POSE satellites have been flying essentially the same instrument suites since the early 80s until NOAA 19 launched in 2009. So with the exception of a few minor changes, my NOAA colleagues will tell me about how they improved AVHRR, but it's essentially the same thing for 20 years, which is how you can afford to keep doing this. It's very expensive to build one-of-a-kinds. So if you're a NOAA, you're going to want to build, you have to keep making these measurements, so you're going to try to build them as efficiently as you can, so you try to build the same thing. And because one, your primary users for NOAA are the weather centrals, and they want the same data, and so the better part of JPSS is that we know it's out there, and from a science perspective, we know we're going to get the data sets for the next 20 years.
All right, any other questions? Oh, one more. I think we have time for one more.
I know that everything at NASA, takes a huge team of people to build. It's not just the people out front. So I was wondering if you could speak to, how the size of the team and just, what they do.
The team is at multiple levels. So an instrument team, Scott, how many people did you have building OMPS? 120. Okay, so you had 120, and that ranges everywhere from essentially optical designers to a scheduler and a configuration management person. All these people work on the team. The Veers larger instruments were probably in excess of 300. So you're sort of in that. So multiply that times 5. Spacecraft, another 100 or so at the spacecraft. NPP, probably 150 on the NPP project. Now you got to throw in the Raytheon ground system people, 450. People at the archive, the weather centrals, all who are part of the team, all adding up. So round numbers, what are we at, 1,000? You know, something like that, just sort of one significant figure. Right. So easy. So that's why there are 800 people coming to watch. And it was on a weeknight.
All right. I think that's all the time we have for questions for Jim. Thank you, Jim. Okay, our next speaker is Janice Smith, also from NASA's Goddard Space Flight Center in Maryland. Janice has been working on the data processing system for NPP and for quite a number of other missions that have come out of Goddard. I see here that worked on the data system for one of the Space Lab missions. Also for the UR satellite, which made headlines recently as it came down somewhere in the Pacific Ocean, we hope. So Janice will talk to us about I guess really where the rubber meets the road for NPP is delivering the data, how it gets out to people. Janice?
Thank you. As you've heard, that the NPP mission is actually a mission to monitor the health of Earth from space. Obviously, it's continuity for NOAA and NASA in different capacities. For NASA, this is a continuity mission for, as you've heard from Piers and Jim, both for the climate research, Earth science climate research. For NOAA and also for the DoD, it is appropriate for them in terms of doing weather forecasting. So you've got dual objectives, and also there's special events, as you heard, hurricanes, fires, and things like that are also very key to the activities that are going on, but the service that NPP will bring to bear to both the science and weather forecasting communities. NPP is actually going to be launching this evening, early tomorrow morning, and it will get launched and inserted into orbit and ultimately will fly at 512 miles above the Earth. It will go through 14 orbits a day, so of about 101 minutes orbit per day, and the satellite will collect scientific data from the 5 instruments, as well as health and safety data from the instruments and the spacecraft. A little nuance, we refer to the spacecraft as the bus. The 5 instruments we're collecting the science data equate to a satellite. So when we say satellite, we're talking about the complement of the payload and the spacecraft itself. With that, once we get into orbit, we'll go through a 90-day checkout period, activating the bus first, and then incrementally bringing on the instruments till we have a fully functioning satellite at the end of approximately 90 days. Once we're in orbit, though, the rocket has done its service and we're now in place, we go through a series of command and control activities, as well as data processing on the ground. So while we talk about the flight system being about the spacecraft, we call it the space segment, and the launch services, the launch support segment, which is for the rocket, we now have a ground system that's comprised of 4 segments. The command, control, and communication segment does the commanding of the spacecraft, also health and monitoring, and any kind of loads and software updates that have to be sent up to the spacecraft. We have one ground system, ground station that's located in Svalbard, Norway. It's in the Arctic Circle, about 78 degrees north. and it's a perfect location because it sees the spacecraft on every orbit. So being at that high latitude, it gives us a chance to see it every orbit, and we downlink our science data from that location, routed back to the U.S. for data processing. So we go through our monitoring, data processing, creating data products, as Jim said, of approximately 30 data products that are made available for both the science and the weather communities. Once it comes back down to the C-Cube system, it's routed to the IDPS, the Interface Data Processing segment for data processing, and from there it's propagated further into a science data segment as well as the archive and distribution segment for additional evaluation for climate usage or for archiving and distribution for people that come in and request it. From the IDPS, we also make the data directly available to 2 weather centrals, one for the NOAA NESDIS community and another for the Air Force Weather Agency in Omaha, Nebraska. So from there they can do additional data processing or making the data and their products available to their users in their field, and likewise for the scientific community. Let's see. I think I hit pretty much everything. One other thing that may be of interest to folks is, since we do have the Svalbard ground station is key, we adopted a mascot very early on in our mission. Some of you may have already heard it. Some of you may have seen the little logos. There is a polar bear, since we are in the Arctic Circle. That's correct. We have the polar bear, and he has become a team builder throughout the life of our mission and development activities, and he's been to numerous places, North Pole, South Pole, throughout the U.S. and other continents. He is a team builder in the sense that he's rotated to various members of our 1,000+ individuals and has made their trips at various locations and travels around the world. And I think that's it. Sure.
Thank you, Janice. Let's see if we have any questions. Start over here.
You mentioned briefly sort of the prospect of sending various firmware or software updates to the satellite. Can you talk a little bit more about sort of what that process entails?
Well, we have to continue to monitor the satellite and the instruments as we go through mission, and at some point in time there are changes in degradation potentially of the instrument or fine-tuning. So we do go through an upload, table loads, software loads that are provided by the various instrument teams and folks doing calibration and assessments as they go through algorithm data processing on the ground. So at that point in time we get upgrades to those tables and provide them through to our command and control center, the Mission Operations Center in Suitland, Maryland at the NOAA Satellite Operations Facility, and then they are uploaded via the ground station to the satellite when it's in orbit, when it's in view of the coming over the Svalbard site.
Hi, just like my system, I do multiple backups. What do you do in space when you're doing an upgrade and you're in the middle of it? Is there a backup system on board, or several, or redundancy? How does that work?
There are different loads in the system where we don't necessarily directly load these tables into we load it into a separate storage area so we can check that out before we migrate. So there is a redundancy on the spacecraft in terms of making sure we haven't eliminated our operational tables to begin with. So you go through that and make sure that it's working beforehand. And we also have the capability to check out those loads on the ground with our flight vehicle simulators on the ground before we load them up, so we have some confidence in that as well.
Other questions?
Hi. You mentioned that data goes from Norway to the United States for processing.
Yes.
During that trip, is there any type of error checking that happens, and that way we can be sure that data coming from the spacecraft down is correct and going across is correct as well.
Right. We do have error checking, Reed-Solomon coding, so we do have a data check, so we know that what was sent and what was received. We have the way to validate we've received everything.
Okay. And can you speak as to how long it takes for data to be processed from the United States to becoming open to scientists and other people?
Well, let's see. There is, it depends on what community you're talking about, but if you're talking about getting the data directly in from the archive segment, there's about a 6-hour delay in terms of the data processing to point what's available in the archive, received in the archive data system. From the point of observation on the spacecraft to data products out the back end of our system is approximately 140 to 180 minutes. So by the time that the data is being downlinked from the spacecraft, it's already being routed transatlantically fiber back to CONUS, so that we have the ability to start processing before we've even completed the contact at Svalbard. So it's we're already processing the beginning of that particular downlink before we've even received the end of the pass.
And this is all part of the Open Data Initiative by NASA, right?
Open Data Initiative, I'm not sure exactly in terms of the data is available to the public in the archive, but we also have direct users that we propagate the data through to in terms of the Air Force Weather Agency, the NOAA Weather Central, and the Science Data Segment for evaluation for climate research. Those, as Jim was mentioning, are selected instrumenters and science members.
Thank you.
Sure.
Both you and Jim have talked about the archive and how the data gets more important as it gets older. How do you plan for that kind of archiving? How do you plan for having data from 2011 being available in 2040 from an IT perspective?
Well, there is certainly an upgrade process, a technology refresh that, in this case, NOAA has to go through in terms of the archive and distribution segment, which is part of a larger comprehensive data archive. And they've got data in there from many other programs, as well as what will be NPP going forward. So they have the need to archive data for perpetuity, in perpetuity. So you have the data available. It becomes a matter of how you store the data in terms of the data format, the metadata for its easy access and research extraction.
Thank you.
Mm-hmm.
Okay, any other questions? Oh, here we go.
Hi. So, as I understand, this was initially, NPP was initially going to be the first generation of a collaboration between NOAA and the Department of Defense, and now that's not quite going to happen, but you're still going to share some of the common ground infrastructure. And can you talk about some of the things you'll be testing and learning on the ground as part of that collaboration or not?
Well, actually, at the beginning of the program for NPP specifically, it was a partnership between NOAA, NASA, and DoD. Since the NPOS program has been altered, the JPSS is actually looking at only the future JPSS, which NPP is the predecessor for, is responsible for the afternoon orbits now. And so our architecture, our mission system architecture already included many of those aspects on the ground. So in terms of interface definitions and concepts of where these physical locations and the processing capability at these other sites have been in place and being tested throughout the life of the development effort. So we have in the future going forward, there would be the potential for 2 additional DoD weather centrals to be added into the mix that we have the 2 for NPP. So that is a continually evolving development effort. So while NPP ground system is developed and will be upgraded as we move forward into the next generations of those satellites. So in a sense, we're continually testing, implementing testing, and bringing online different capabilities.
We have 2 questions from Twitter, one from Navy Singer 117, and it's, can you explain how one can gain access to the high rate data capability of NPP?
Oh, the HR, okay, high data rate capability. Let's see here. Let me go back and explain what that is first, and and then we'll see if we can answer the real question. There is also a capability on the NPP spacecraft for high data rate broadcast, direct broadcast, for people that have regional data systems or antenna systems. We have the ability, or they have the ability, to collect data in real time as the satellite is passing over their particular locations. They have the capability of the equipment to receive that data. So many of the universities and some of the other regional users that feel like they need and want the data for their particular region can receive that data in terms of accepting it. It's not the science downlink that is directly for Svalbard, but there's another antenna system on the satellite. This is the science mission downlink, the high data rate broadcast that's continuing in real time throughout the life of the mission, and then the TDRS antenna as well for communications as need be. This is the high data rate antenna system, of which people that are interested have the ability to generate their own receive stations and collect that data. In terms of the details for setting up that type of capability, there is information on the website for that, but I don't have the specific details at hand because it's more of an external capability for those that want to go. But we do have the information on the website. The website being npp.gsfc.nasa.gov, and there is also a link to the direct readout capability web location that gives you more information about that.
About 50 to 100K for regional
station. Okay.
We'll put that website up on the Twitter feed as soon as I sit down.
Sure.
Yeah, there's another question from Twitter, and that is from the real JD Flux. What type of systems are used to process the NPP data? Linux, Unix, Windows, supercomputers?
Well, that's a combination. Right now, and we're going through evaluation. Oh, yeah, that's more of a technical question. We're IBM based, and we are. I don't have the details on that. I might have to. It's mostly IBM based for the interface data processing, where the data products are actually generated. We are looking at as we go forward with some additional upgrades and enhancements, but the base system that we have now is IBM based.
Okay, I think we have time for one more question. Did you have a question? Okay.
Well, I wanted to know, as an expert, where do you get your weather reports?
Well, it probably depends. When I'm watching the local news at home and being in the Washington, D.C. area and close to Goddard, there's frequently the weather reports on the news, and it's always, oh, there's one of our satellites. Otherwise, it's frequently, we'll go to the weather channel websites or other websites and some of the NASA Direct websites. The information is there.
Okay, thank you. Thank you, Janice. Okay, our next speaker is Scott Asbury, and he is Senior Program Manager at Ball Aerospace and Technology Corporation in Colorado. They built NPP and a lot of the instruments that are on it. Scott specifically, I think this was mentioned earlier, worked on the ozone measuring OMPS instrument on the satellite. And he's going to talk a bit about how you build a satellite and the instruments that are on NPP. Scott?
Thank you. Good morning, and we provided a handout that you can pull out and look at, and we can talk about how we actually build a spacecraft. It took about 3 years to build the basic NPP spacecraft bus, as we call it. And from that point, we began to integrate instruments as they were delivered to the spacecraft over the period of about another 3 years. So when you look at the photos, you can see that the first thing we do is we build a structure called the bus. And the bus is basically the basic spacecraft minus its instruments. And once the bus structure is built, there's a wire harnessing that goes on. So that is putting all the wiring into the spacecraft to talk to all the instruments and all the other systems. on the spacecraft. The spacecraft subsystems that are integrated, they include things like avionics and batteries, computers on board, the systems on the spacecraft that operate it, the telecommunications system that control the S and X band antenna systems. And those are integrated. We have a star tracker on board, ball-built star trackers that basically track the position of the spacecraft as it flies along. And on board the spacecraft are reaction control wheels and torque rods. And what those do is those keep the spacecraft properly oriented and accurately pointing at the Earth. Pointing requirements and pointing knowledge and stability is extremely important. The spacecraft does not want to be shaking as it flies along. That would result in blurred images. So it's what we call jitter, has to be controlled as the spacecraft flies along. We have a propulsion system on board that's used for orbital maintenance, and it's also used at the end of the mission for a deorbit burn. So you've heard about spacecraft re-entering recently out of control, not knowing where they're going to hit. When NPP is decommissioned on orbit and its life is over, the propulsion system will be used to target a specific area over the ocean, and that's where the spacecraft will be dropped in a long, long time from now. So, yeah, the solar array is what provides the power for the spacecraft. So it's folded at launch, stored up against the side of the spacecraft, and that solar array is deployed shortly after launch. It's an automated deployment sequence. So one of the first things you want to do once you separate from the launch vehicle is to get in a positive power mode, get the spacecraft properly pointing and oriented, get the solar array pointed at the sun, and begin to generate power, because the batteries on board the spacecraft will not last very long without the ability to replenish them by generating power when you're in the sun. The spacecraft solar array, that's probably one of the things I worry about the most, because if it doesn't deploy, you don't have a mission. So there are multiple automated deployment attempts. So if it doesn't deploy initially, there will be another attempt a few minutes later to automatically deploy that solar array. Once the bus is done and all the systems are on board, then you begin to integrate instruments over time. Basically, it's about a 1-month center for integrating instruments. So there's 5 instruments, so you could, if all the instruments came in right on time, you could integrate all 5 of those instruments in about 5 months of time. And the instruments that were integrated, the first was ATMS that Jim talked about. That was built by Northrop Grumman. Ceres was also built by Northrop Grumman. That was integrated second. Then OMPS was built by Ball Aerospace and the team I led. It took about 6 years to build OMPS from beginning to end. So it was, it took quite a while to do that. VIRS, the Visible Imager, which is a huge instrument on the spacecraft. And it's the main reason the spacecraft is shaped like a wedge. That instrument is so large that we had to design the structure to accept the instrument that you can see on the front. We had to design the structure to accept the instrument and still fit within the Delta II fairing. So that was the driver for why the spacecraft is shaped the way it is. The last instrument integrated was the cross-track infrared sounder. That was done in mid-2010. So once all the instruments are on board, from that point to launch is approximately another year to a little bit more than a year to do what we call the full satellite level testing once all the instruments are aboard. Then we take the satellite and we basically subject it at the satellite level with all its instruments to what it's going to experience over its life, both through launch, the ascent phase, the release, and then its on-orbit phase. So we go through vibration testing. So this simulates the launch loads with margin. So what we do is we actually subject the spacecraft and all its instruments to more force or more loads than it will actually see in the launch vehicle, and that gives us margin and the confidence to know that our design is sound and the spacecraft will withstand the launch environment. We also do acoustic level testing. Basically, launch vehicles, as you'll see tonight, I guess, tomorrow morning early, they're quite loud, and the spacecraft is sitting right on top of that. So it's going to experience, you know, in excess of, or right around 140 decibels of sound. That's quite loud. So what we actually did is we set up 144 rock concert speakers around the spacecraft. You can see that in your picture. We blasted it with 144 decibels of sound, and that amount of acoustic energy is actually unbelievable. You don't want to be around it when it happens. It's absolutely deafening. After that, we go to the electromagnetic interference, or EMI, EMC testing. And what we do is we basically turn all the systems on the spacecraft, all the instruments on, and then we hit it with electromagnetic energy. And we make sure that the electronics in the instruments and the systems don't pick that up. What you don't want in your design is you don't want to design an antenna in your instrument, not knowing you did that, and have that pick that signal up when another instrument's operating. If you do that, you can actually absolutely get bad data out of your instrument. So we run a lot of tests to make sure that our EMI, EMC compatibility is correct and that the instruments will perform their mission and the spacecraft will operate as planned. After that, we go into a large thermal vacuum chamber. So we put the satellite down into a very large chamber, and we flood that chamber with liquid nitrogen. The shroud actually goes down to about minus 190 C. The spacecraft doesn't quite get that cold, but we put it down in there. We do it at vacuum, and then in a vacuum, we sit and we cycle the temperature up and down. And as we're doing that, we'll go to a cold state and hold and operate the systems and make sure they operate properly in the cold. And then we'll turn and alternate to hot, and we'll operate the systems as we do that, and we'll monitor the systems on board. As you can imagine, very large thermal gradients across the spacecraft and the instruments, but you want them to stay in focus. You want these pretty pictures from Piers that are properly focused and properly pointing. You have to design your system and the structure and the optics and the mechanisms so they continue to operate over wild temperature extremes. After that, then we pack the satellite up and we drive it all the way from Boulder, Colorado to Vandenberg Air Force Base. And if there was one job I wouldn't want to have on the program, it's the truck driver. Because you're driving a satellite worth $1.5 billion down the road. It's not something I'd want to do. The satellite arrives here at Vandenberg, just a short distance from here, and that processing goes on to make sure the satellite survived its trip from Boulder. And we fuel the spacecraft, the propulsion system gets fueled, and we get it ready to move it out to the launch site. It gets put inside a canister or a can and wrapped up and protected. It's driven out to the launch complex, and it's hoisted to the top of the Delta II rocket, and it's bolted on. And it's last thing we do is we pull off all the removed before flight tags that you see on aircraft. We have those on satellites too. We vacuum it, believe it or not. We clean it up. We make sure it's pristine, and we close it inside the fairing. And the next thing it will see is we'll see space when the fairing releases after launch. So it's pretty exciting. Jim talked about paper. Yes, we generate paper. And you know it's time to launch when the weight of the paper equals the weight of the satellite. And that's about the size of your SUV, 4,500 pounds. So the power on board is about 2,500 watts. And if you want an idea, is if you buy a Coleman generator or a backup generator and put it up beside your house when the power goes out, you're probably generating about 2,500 watts to run your refrigerator and your computer and your TV and a few lights. So it's not a very high power system, believe it or not, because you have to generate all this power in space through these solar panels. So with that, I'll be happy to take questions about building an instrument, building a satellite.
Scott, any questions? Right.
In the handout and the labels, you talk about installation of electronics, but integration of instruments. And I'm wondering if you can talk about what those two words mean to you,
right,
and how they're different from how we might perceive them.
Right, so the electronic systems on board the satellite, there are actually quite a few different boxes, as we call them, and they're all basically black boxes that we bolt on. They're everything from the command and data handling system to the attitude determination and control system. They're all the systems that make the spacecraft operate and live, the systems that we have a spacecraft control processor on board. It's a RAD 750 computer on new satellites on NPP. It's even an older generation processor. There's a solid state recorder on board. So as the instruments are generating data, they're feeding them into the spacecraft in a solid state recorder. And so those are all boxes that get installed or bolted onto the spacecraft. These boxes are designed to just to be bolted on and hooked up electrically. An instrument is a pretty delicate thing that we do. So as we go through an instrument integration process, there's a lot of care taken in the handling of those. There are when we install boxes as well, but the instruments are pretty special. Veers cost a lot of money. The instruments, each instrument can cost close to the same amount as the actual bus. So instruments are where all the a lot of the expense is on the satellite. So we treat those with kid gloves, and when we integrate them to the spacecraft, we have to make sure that they're absolutely aligned where they need to be. We have to know when we put them on the spacecraft that they're aligned down to, thousandths of an inch, and get them exactly positioned. So that's probably a little bit of the difference, is when you get into integrating instruments, you're into extreme precision.
Okay, next question.
Since precise instruments are very important, and obviously you don't want your hard drives to fail, do you make your own hard drives? Do you use commercial hard drives? Do you use special super space hard drives?
It varies. Actually, what we do is we use a combination of commercial items that we will go procure and then qualify for space. And there are vendors out there who build items that you may find, like the batteries, for example, or lithium-ion batteries. It's the same battery you have in your laptop, basically. We use, I know on JPSS, which I'm starting the process of building right now, we're using Sony batteries. And there's a company called ABSL that will take those batteries and they'll integrate them into a large, so you take a bunch of those battery cells, like in your laptop, put them together to a lithium-ion battery, and then you test them and qualify them. They've done that before, and they have flown in space, so those are space qualified. So you might start with a product that's built for a regular application, and then you might, what we call upscreen, or qualify that for space flight. Other things are built specifically for space, like mechanisms. They may be designed specifically for a space application. So it varies, it really does. And we have a lot of vendors. Ball doesn't go build the guts of the electronics. We buy a lot of the systems and then integrate those. We do build components. We build the star trackers. We build the structure. It just really varies. But we buy a lot of things and bring those in. And part of the process of building a satellite, while it takes so long, is just the procurement process alone can take a year to a year and a half from order to receipt of the item, because we ask our vendors to actually test the items at the component level. So it's kind of a spiral development as you build a satellite. You build and you test and you build and you test and you build the system up, up, up. You don't wait to the end as you go. And so that's part of what generates a lot of that paper, because somewhere down the road, if you have a problem, you may have to back up and figure out, why is this problem occurring? Where did it happen? And we trace all the way, every part's traced to its lot date code, to where it was manufactured and when. We can trace all the way back. NASA has a system in place called actually a guide-up system, where they can basically go, if a part has a problem somewhere on another program and they determine that problem's systemic to the part, they can send out an alert and they can say, check these parts with these lot date codes, and we can pull out our documentation and say, oh, yeah, we got one, we better look at it. Or no, we don't have any of those, we're good.
Okay, we have time for one more question for Scott.
I'll try to make it a good one. About the star trackers, two-part question. Number one, what stars does it use to keep itself aligned? And number two, who's responsible for watching that and making orbital corrections down the line?
So the star trackers themselves, they basically look at the star field. So they don't look at, they look at the whole picture, the scene they're seeing, and they can use that to figure out exactly where you're pointing. Those star trackers are built by Ball Aerospace in Boulder, so that's one of the things we did. We built most of the star trackers that flew on the shuttle. We've been building those for a long time. The data that comes from the star tracker feeds into the attitude determination and control system. So what it does is it looks at that data. It compares, it looks at the star tracker data. We also have an inertial reference unit on board that basically says which way's up. And of course, up's relative in space, but it tells you which way you're pointing. And all that data is continuously fed into the spacecraft systems, and it will correct itself. Spacecraft can also be controlled from the ground as well. not burns. Those are usually the reaction control wheels operating inside the spacecraft. Those are minor corrections. Burns are typically not made very often. Those are orbital maintenance burns or a collision avoidance burn. If those have to happen, those are made from the ground. Yeah, we do worry about debris in space and have the capability to dodge it.
All right. Thank you, Scott.
Thank you.
All right, our next speaker and our last speaker for this segment of the Tweetup is Tim Dunn. Tim is the launch director at NASA's Launch Services Program based at Kennedy Space Center. He's the guy that's in charge of getting these rockets, like the Delta II, which he's worked with extensively up into space. A couple of the missions that he's worked on recently, you might have heard of, the Messenger mission to Mercury and the Kepler Astronomical Observatory. So Tim's going to talk to us about how NASA deals with, they're called Expendable Launch Vehicles. ELV will be the acronym you'll hear. You got to know the acronyms if you're going to know what NASA does. So Tim.
Thank you, Steve. Good morning. Okay, this is my first tweet up. So bear with me and help me along. You guys have done this a lot, right? Well, I'm glad to be here today. Very excited to be here at Vandenberg, ready just less than 1 day away from launching the NPP spacecraft. That is very exciting for our launch team. I'll tell you just a little bit about what I do, where I came from, how I got to where I am now. As Steve mentioned, I am the launch director for NPP. My call sign for Launch Countdown is NASA Launch Manager, NLM. So I'm the guy responsible for making sure all of the entities, all of the various elements of our team are ready to go. Contractor, safety, quality, spacecraft, range assets, everything. And so once we're all good, I give the final go, and then we turn it over to our contract launch director and performs that final countdown. This is my second mission as launch director, so that may surprise or scare some of you. So I've been around the launch business for over 20 years, but just recently attained the position of launch director earlier this year. My first mission as primary launch director was on the Grail mission just about 7 weeks ago from Florida. Very successful there, very excited. They allowed me to do the last two currently contracted Delta II missions, those being Grail and NPP, because that's where all my background was. I kind of grew up in the launch business, primarily on the Delta II rocket. So this little rocket is near and dear to my heart, and I'll talk to you guys a lot about that, and I'll be glad to answer a lot of questions on the rocket. Started out my education back in the 80s. Proud to say I'm a graduate of the University of Alabama. So we've got a little bit of a game we're looking forward to in a couple of weeks against some Bengal Tigers from LSU. So if you can tweet anything about Bama or Crimson Tide, I'd appreciate it. Got an electrical engineering degree. The Air Force helped get me through school on an ROTC scholarship. So went off and served 9 years with the United States Air Force in the space segment. I got to fly GPS satellites in Colorado Springs. So I was on the in the master control station for GPS. So I was there flying the very last of the old GPS satellites that were launched here from Vandenberg back in the 80s, or late 70s, early 80s. And then I was able to see the very first GPS as we know them today, the first Block A satellites launched on February 14th of 1989 from Complex 17 in Florida on a Delta II rocket. So Delta II has been very good to me personally. It's been very good to our nation, and I'm sure it's touched all of our lives. You know, I like to say that Delta II has sent rovers to Mars and put GPS in our cars, because I'm sure we all have a Nuvi or a TomTom telling us where to go these days. After some time in the Air Force made the mistake of sending me around various assignments, but then they sent me to Cape Canaveral and put me on the Titan IV launch team, and that was when I was hooked. Launch was it for me, and I knew that was the segment of the space industry that I wanted to stay in. So I did 3 years on a Titan IV launch team. Got to launch a few of the big rockets, and then I transitioned over to the civilian workforce. Worked for McDonnell Douglas for 5 years on this little baby, the Delta II rocket. Launched a lot of rockets as a guidance engineer for McDonnell Douglas. Then had the opportunity to come back with the government in 2000, so 11 years ago now. And came on with NASA then, and worked my way through various positions. Most recently, before I was launch director, I was a vehicle systems engineer, so working with all of our various engineering elements, the various disciplines of engineering that we have to assure readiness of the rocket. And that's how I got to where I am today. So very happy to be here. Launch director is a thrilling job, and it's you have it's a lot of excitement, but it's also a lot of pressure at times. You feel a little bit of the weight of the agency on your shoulders at times. They task our position. I work for LSP now. Let me get that out there, Launch Services Program. So within LSP, we have 2 launch directors, myself and Omar Baez. So while I'm focused on this rocket and this mission, Omar's backing me up. So you'll see him on NASA TV sitting to my right. So making sure that I'm doing all the right things. Omar's been around the launch director business for about 10 years now. So well-seasoned launch director. And he's off focusing on his primary mission in about a month from now, the MSL mission from the Cape on an Atlas V. So we're very excited, very busy at Launch Services Program right now. So let me talk a little bit about what LSP does. You guys may have heard LSP. We use that acronym for Launch Services Program. The NASA agency, or the NASA organization within the agency that I work for, we broker the business between the spacecraft community and the launch vehicles. So we put all of the launch vehicles that are domestically available in the United States in a bidding process, and they are able to get onto what we call the NASA Launch Services Contract, NLS. And that enables them to then be qualified to compete to launch all of our spacecraft community's assets. So when one of our spacecraft customers comes to us and says, I want to launch in 2014, 2015, we say, great, let's go look at the stable of rockets that are qualified to launch you. Then we open up the bidding, and then those contractors that are qualified to bid for that can bid for that service. So NPP came to us many years ago. They were of the weight and range that a Delta II vehicle was ideal for them. Went through that process. We awarded United Launch Alliance, ULA, which is builds the Delta II rocket, also builds Atlas V rockets. We awarded them the contract to launch NPP. A little bit about, let's see, what else would you guys like to know? Let me talk a little bit about NPP itself. I'm going to give you some numbers because it's fun to tweet some numbers out there. NPP is going to be the 357th Delta launch. So that goes all the way back to May of 1960. So a lot of Delta launches. Now that obviously is the original version of Delta, Delta I, which launched from the 60s up through 1989. That includes 150 launches of Delta II to date. So NPP will be the 151st Delta II configuration to launch. Of those 151 Delta IIs, NPP will be the 50th NASA mission on a Delta II. So that's significant for us. Yes, Steve?
See if we got some questions. We're just about running out of time.
Okay, sure.
But any questions here? Start with you.
Can you tell us a little bit about the personality of the Delta II rocket? What makes it so good, and so why are we stopping with it?
I guess the personality of the rocket, very dependable, a workhorse for our nation, a workhorse certainly for NASA in the medium lift category. What makes it dependable is the heritage of it, those 356 launches that have preceded NPP, all of the processes and the people that have been building that rocket throughout the years have given it this tremendous success rate that it has today. Why we are moving away from it is economics. We, LSP, look to the commercial U.S. launch industry for our rockets, and right now that industry seems to be moving toward lower prices, trying to obviously get the prices down for their commercial customers and for government customers, the United States Air Force being one. And so ULA, the contractor for Delta II in particular, would like to offer the Delta II if there is the need for it. But satellites have grown bigger, and it seems to be more of the demand that is in the larger class, the Delta IV, the Atlas V class. So, and that's basically the answer. Another question,
Okay,
Steve?
next question.
This launch vehicle is flying in the 7920 configuration, is it?
That's correct.
How does launch processing differ from each version of the Delta II rocket, like with the 4 solid rocket motors or whatever? How does launch processing differ from each launch?
Depending on the configuration that we're in, you mentioned NPP flying in 7900. That means we have 9 solids. So that's an extra 2 days of processing of putting the solids on early. But as far as the solids go, it's nothing more than that. We generally have about a 45-day processing flow on the pad, so you're talking about a couple of extra days. The other configuration changes would have been a few years ago we were flying 3rd stages, so that would have been a 7925 at the end. That would have entailed some additional 3rd stage testing, added another day and a half or 2 to the processing schedule. So overall, it's not a significant lengthening or shortening of the processing schedule based on the configuration.
Okay, we have time for one last question for Tim. Let's go over here.
I know I saw mention of some other smaller craft that were hitching a ride on this launch. Can you talk about any of those?
Yeah, I'm glad you brought that up. NASA is pleased to be launching 6 CubeSats on this Delta II NPP mission. These are also called nanosatellites. They're roughly 4-inch cubes, yay big, and they are mounted on the 2nd stage of Delta II. So obviously our primary mission is NPP. About an hour into launch, we're going to separate the NPP payload. About 20 minutes after that, we'll then eject the first of these series of 6 CubeSats. We put them in what we call P-pods, which is a canister mounted to the 2nd stage structure. And these P-pods will be ejecting aft. There is one P-pod that contains 3 CubeSats, a second P-pod that contains 2 CubeSats, and a third one that has a single CubeSat in it. The universities and students, it's an education program, and we're really proud to host this on this Delta II launch.
Thank you, Tim. All right, thank you, Tim. And while we give a hand to all of our speakers, a lot of great information here. Checking the clock, I see we are now just about 16 hours away from launch. To watch it tonight, it will be televised. Our television coverage begins at 12:01 Pacific. So tune back in about 14 hours. And the launch is scheduled for 2:48 a.m. Pacific Friday morning. So thank you all for watching. Make sure to follow today NASA Tweetup for the continuing activities, and we'll be good to go. Thank you all.